Okay. So, would you like to start? I mean, we're happy to have Romain Tessera, talk about quantitative orbit equivalence.
Thank you very much, Lewis, for the invitation. So yes, I'm going to talk about the subject that you've already heard about by my former student, Amandine Escalier. And so I will try not to overlap too much. And so don't hesitate to interrupt me if you think I'm going too slow or something like that. So let me start with really the basic. Oops. So the objects of study are going to be, on the one hand, a countable group. So you may think of Z, ZD, or the free group on K generators, for instance, and we will see more examples. And the second object, which is important, is a probability space. And here, for instance, you may think of the circle equipped with the Lebesgue measure, the normalized Lebesgue measure, or the what's called the Bernoulli shift, namely the power, of 0,1 to the power lambda, or you could replace 0,1 with another probability space. And finally, what we are going to consider, to put these two things together by assuming that lambda acts on the probability space, preserving the measure. For instance, you have Z acting by rotation on the circle, or as I said, the Bernoulli shift, where you just move the variable. So what we are going to study is going to be these PMP actions up to a certain equivalence relation, which is not the most obvious one, but the most obvious equivalence relation between PMP actions is isomorphism, where you require really everything to be the same, namely that you have an isomorphism between the groups and an isomorphism of measure spaces between the spaces, which intertwines the action. Here we are asking much less, because first of all, the two groups could really be different. They don't have to be isomorphic. And the only thing we require is that what is preserved by the isomorphism of measure spaces is not the action, but the orbits, or if you want, the equivalence relation, which is associated to the orbits. And so what this means is that if you look at psi, it doesn't have to intertwine the action, but it had to intertwine the orbits in this sense. So a first theorem of Dye, which is, I think, from the 60s, if I'm correct, is that two ergodic PMP actions of Z. So here you need to require ergodic, because ergodicity is recognized by the orbit equivalence relation. So the statement says that ergodic PMP actions of Z are orbit equivalent. Now, if you now you can forget about the action somehow and just focus on the groups. And so we say that two groups are orbit equivalent if they admit some PMP actions which are orbit equivalent. So it doesn't mean that all their actions have to be orbit equivalent, but you require only that each one of your groups that has a PMP action, so that these two PMP actions are orbit equivalent. And a very strong and impressive theorem by Ornstein and Weiss from 80 says something much stronger actually than just that all amenable groups are orbit equivalent. It says really the strong version of it, namely that if you take any two countable amenable groups and any two PMP ergodic actions of these groups, then these actions are orbit equivalent. So it's really very, very strong. And it really means that for amenable group actions, there is really nothing that no specific property that you can recognize on the orbit equivalence relation. For instance, being mixing or I don't know, weakly mixing, or these ergodic properties are not recognized. Z and Z square have the same actions from this point of view. So it's very, very strong and very surprising somehow. And if you compare with what happens for non-amenable groups, it's almost the opposite. So here I'm just giving one example among a huge I mean, a huge literature on this topic. But one of the first results of that kind is due to Gaboriau, and it says that if you take the free groups on K generators and K prime, then they are orbit equivalent if and only if the number of generators are the same. But you also have rigidity results for lattices, for instance. So I'm not going to talk about this because this is not really the topic of my talk. But really what I want to convey here is that amenable groups are really a special word, and non-amenable groups are almost the opposite word in some sense. So now the question is really that, is it the end of the story for amenable groups? Because, you know, it sounds like orbit equivalence does not see anything. So should we just give up and forget about orbit equivalence, or should we try maybe to, you know, try to understand a little bit what happens? Like why orbit equivalence rubs out everything about the geometry, for instance, of the group. And by asking this question, why, I mean how somehow. And how it means that maybe you can see the process by refining a little bit what orbit equivalence means. And by which I mean that, you know, in an orbit equivalence, what you have is an isomorphism between the spaces, which intertwines the orbits and not the group actions. So, you know, maybe there is a way to quantify or to try to measure how distorted somehow these identifications between the orbits is, is obtained from the orbit equivalence. So by which I mean that we may add constraints on the orbit equivalence relation, which I'm going to explain very quickly. And on the other hand, if we really want to understand what's happening in this phenomenon, we may also try to, you know, measure how groups can be different, amenable groups. So for instance, Z, you want to say that it is more amenable than ZD prime, that D, if D is smaller than D prime. And in the same spirit, you'd like to say that the risk product of Z with Z is more amenable than the risk product of Z mod 2Z with Z, and so on. Here, because I'm going to often give examples of risk product, let me just remind you what the risk product is. So the risk product of two groups is a construction which is very convenient to construct, especially solvable groups. So it's obtained in the following way. It's a semi-direct product where B is the group which is acting, and the normal subgroup is just a direct sum of copies of A indexed by B. And of course, you have that the action of B is by translation on this index set.
Romain,
Yeah.
Lorenzo has a raised.
Yeah, sure. I mean, please don't hesitate to interrupt me and ask questions. But I don't see.
Yeah, I was a little surprised about that theorem about you know, all amenable group actions are orbit equivalents, because I thought that there was this whole big structure that Giordano, Putnam, and Scow had about ZD actions on Cantor sets and their orbit equivalence relations. Or was that, or is that topological versus measurable orbit equivalence?
Yeah,
their actions are equicontinuous.
Yeah, exactly. So indeed, I mean, if you consider continuous actions on the Cantor set, that's a different story. Like things are really different. And as you say, here really the fact that we only consider measured actions means that, for instance, if you have singular points or, you know, singular orbits or something like that, you don't see them if they are of zero measure. So
okay,
that's essentially what's happening. So here the measure doesn't see the difference, if you want, but the topology sees it.
But also they only address profinite actions, profinite group actions. So if you have a tiling space topological action, they don't address that either. I mean, that's in between the case here of ergodic and the equicontinuous cases.
Yeah. Yeah.
Okay.
Thank you for your.
Okay, thanks.
No, thanks for your question. Actually, don't again. Please feel free to ask any question you like. Yeah. So now let me try to do the first thing, namely quantifying orbit equivalence. So one way to do it is the following way. So when you have an action, a free action on a probability space X mu, then you know you can define a world distance on X. By which I mean that basically what's happening here is that X is like, I mean, setwise, is just a bunch of orbits of lambda, and lambda, because the lambda acts freely, just a bunch of copies of lambda, if you want. So you may just, define a metric, which is just the world metric on lambda, and you just decide that the distance is infinity when you are just jumping from one orbit to another. So that's essentially the definition that I'm giving here. It's a very naive one, but it gives you, well, a distance which may equal infinity on your measure space. And now that you have this distance, if you have an OE, an orbit equivalence, what does it mean? An OE is a map that sends orbit to orbit. So, I mean, by definition, an OE satisfies that the distance between a pair of points for one action is finite if and only if the distance for the other action is finite too, because you are in the same orbit, and being in the same orbit precisely tells you that the distance is finite. But now, if we want to be a little bit more explicit, we may try to quantify the distortion, like the difference, if you want, between these two distances, the one coming from one action of one group and the one coming from the other action of the other group. And so one way to do it is comparing, if you want, how distorted it is when you go from one group to the other. And so here you may assume, for instance, that the distance, so you have a map, which given an element lambda in your group lambda, gives you the distance between X and lambda X measured in the world metric for gamma. So, and now what we are requiring is that if you integrate over X, like for instance, the power P of this distance is finite. And clearly, I mean, you see that there are two directions. And I mean, there is no reason a priori why we should require the same condition on one way and on the other. From lambda to gamma, you may want to assume some integrability, and on the other direction, you may want to assume another integrability. And that's actually something which is quite interesting of its own, but I'm not going to address it today. I'm just going for simplicity only to assume that the degree of integrability is assumed to be the same on both directions. Yeah. Oops, sorry. Yeah, so let me state a first important theorem by Lewis, which is from 2016. Well, yeah, is there a question? No. So yeah, sorry. Yeah, so the first geometric invariant, if you want, that quantifies amenability is the growth function. Okay, the growth function, I mean, of course, if a group has a larger growth function, you may think that it's less amenable. And so this first theorem tells you that if you have an integrable orbit equivalence or L1 orbit equivalence, then the volume growth have to be the same. So in particular, it implies that if ZD is L1 OE to ZD prime, then of course D equals D prime. And to complement somehow this result by Bowen, you have a result by Austin, which I'm not going to state in full generality here. I'm going to come back to it at the end of my talk, which says that if lambda is ZD, and if you have a group which is L1 OE to lambda, then this group has to be itself virtually ZD. Actually, the theorem by Austin is about nilpotent groups in general. And for instance, if you take the Heisenberg group, which has the same group as Z4, the Heisenberg group has growth exponent 4, then, I mean, by this result of Austin, you can conclude that the Heisenberg group and Z4 are not L1 OE, although they have the same growth. And we shall see that this precise result is actually I mean, for this precise result, L1 is really optimal. I mean, I'm going to be more specific about this. But what I mean to say is that if you relax a little bit the L1 condition, then you will have interesting things happening. So I've just defined LP orbit equivalence, but you may realize that there is no reason why LP would be more natural than anything else. So by which I mean that you may just take any increasing function phi and define phi integrability in the following way. And clearly, I mean, this gives you a whole range of conditions, which is, the faster phi tends to infinity, because clearly the only thing that matters here is the values for which phi is big, because you are integrating over a probability space. So the only thing that matters is when phi becomes big. And so the faster phi tends to infinity, the stronger the condition is going to be. For instance, of course, the strongest possible condition is just bounded, mainly meaning L infinity OE. But then if you take a very fast function like exponential, then that gives you a stronger condition than L1, for instance. And L1 is stronger than L1 half, which is also interesting. And you may also consider log, a logarithmic integrability condition. So what I'm saying here is that, the result by Ornstein and Weiss tells us that any pair of amenable groups are orbit equivalent. So you may assume that for very, very, very extremely different groups, like Z, for instance, and a very complicated, huge solvable group, well, the integrability that you will have to find is going to be very, very low. It's not going to be L1 or L1 half or anything like that. It's probably going to be a very, very slow function tending to infinity. So that's why you really need, if you want to understand what's happening in this Ornstein and Weiss theorem, you really need to consider all possible functions, and especially very slow ones. Okay, so I was telling you that one of our goals also is to quantify amenability. And so, I mean, growth function is a very nice and very interesting tool to do it. But a lot of groups have exponential growth. So if you want to distinguish between them, well, you have to find another criterion that measures amenability. And one of them is particularly well suited for this goal, because it's basically what defines amenability, namely the Folner function. And the Folner function, well, it's defined in the following way. So the Folner function, sometimes people define the isoparametric profile, which is some kind of dual way of defining, defining the Folner criterion, if you're quantifying the Folner criterion. So the Folner function, what is good about it is that it's a volume. So it has the same, I should say, the same homogeneity as the volume growth. It's nicely compared with the volume growth, because you see it is the minimal size, so minimal volume of a set, such that the Folner ratio is less than 1/n. Amenability, as I was saying, is characterized by the fact that the Folner function is finite for every n. And of course, the general philosophy is that the faster the Folner function grows, the less amenable the group is. And I was telling you that somehow there is a nice comparison between the volume and the Folner function, due to the fact that they have the same nature somehow. And this is really implemented by this inequality, which is quite famous, the Coulomb and Self-Cost inequality, which tells you that the volume growth is always at least equal to the Folner function. So in general, actually, what happens is that the Folner function is much, much faster than V. It can be as fast as you want. So let me give you a few examples. For instance, when G has polynomial growth, or is polycyclic, or Lamplighter, or even the Gomsack solitaire groups, then the Folner function is really equal to the volume growth, meaning that in most examples I gave here, it's exponential. But as soon as you start taking bigger groups, like for instance, instead of the Lamplighter, you take the risk product of Z with itself, then it starts growing faster than an exponential. And here, for instance, it's n to the n. And if you iterate the risk product many times, then you get n to the n to the n. So it can really be very big. So the first results that we obtained with my colleagues, Delabie, Koivisto, Maître, is that, which is the analog of Lewis' theorem for the Folner function. It tells you that if you are L1 OE, then the Folner functions are the same. But actually, there is something in a way more interesting that we can say about this Folner function, which is that if you have a phi OE coupling between, orbit equivalence between lambda and gamma, for some concave increasing function phi, then you have this inequality. So you see that here it's only interesting when phi is sublinear, because if I grows linear, yeah, sorry. So because you see that if phi grows at least linearly, then clearly, the first statement is just, what you want to know. The Folner functions are the same. But somehow when phi becomes slower than linear, like for instance, if you have L 1/2 OE, then what it tells you is that, well, you cannot say as much as saying that the Folner functions are the same, but you can still get some information on the Folner function. And by the way, if you use exactly the same proof as Lewis' proof for the volume growth, and you can actually get a similar statement for the volume growth. I mean that you also have some information on the volume growth of your two groups. So let me give you an example, very concrete one. For instance, if you have that D is strictly less than D prime, then what you can say is that, no, sorry, this is not the right corollary. What the corollary of this would tell you that ZD and ZD prime are not LPOE if P is strictly larger than D over D prime. I'm sorry about that. I was anticipating another. So yeah, what it tells you. No, sorry. I'm sorry about that. I'm just confused. So okay, so if you have that ZD and ZD prime are LPOE, then this forces P to be at most D over D prime. And here, if you look at it carefully, you see that P is strictly less than 1, precisely. And similarly, if you have an exponential, a group with exponential growth and Z, then if they are phi OE, then necessarily your function phi has to be at least at most logarithmic. And here comes somehow the statement that we are looking for. It also tells you that for any group which is amenable and any increasing function, as slow as you like, you will always find an amenable group which is not phi OE to lambda. So that really gives you somehow a quantitative limitation of Ornstein and Weiss theorem, because it tells you really that you cannot find a uniform integrability condition that would work for any pair of groups. Okay, so now that we have this obstruction, if you want, for integrability conditions of OE between two groups, namely, if we know that now that if you have two groups which have a very different Folner function, then they will not be easy to couple somehow. The integrability condition that you can achieve is not good. Now we want to, to ask the opposite question, whether you can produce good orbit equivalence couplings between some actions of groups. And in particular, what we are interested in, for instance, is whether this obstruction that we found with the Folner function is sharp or not. And the same question would actually be interesting also for the volume growth. So the question now is to find a way to construct couplings. So, you may tell me, well, Romain, come on, there is a way which is already implemented, which is Ornstein and Weiss theorem precisely. But the problem of Ornstein and Weiss theorem is that it is far too strong. In a sense, Ornstein and Weiss theorem is giving you a coupling, an orbit equivalence coupling between any pair of actions of groups. So that's so strong that actually when you look at the proof, I mean, you realize that there is no way you're going to do something quantitative with this proof. At least, I mean, no way, maybe I shouldn't say that, but at least, I mean, I tried a little bit and I couldn't see anything that could be made quantitative in this proof. So if you want to understand orbit equivalence couplings between amenable groups in a quantitative way, you need to find a different approach. You need to find different constructions. And I also warn you that these constructions are not going to produce OE couplings between any pair of actions. It's only going to construct certain actions which are going to have a good integrability, I mean, which are going to be OE with a good integrability condition. So the first construction that was explained in, I think, in details by Amandine last time, so I'm not going to spend too much time, is a construction which is combinatorial and which produces you, in most cases, actions which are profinite. So it's not always the case, it doesn't have to be the case, but in most cases we apply it going to produce profinite actions. So the basic data that you need here is a sequence of finite subsets such that each of these finite subsets are left Folner sequences for gamma. And each Tn is obtained as a union of right translates of Tn minus 1. So it's like if you want a sequence of tilings which are refining each other every time. Because Tn is obtained as a union of right translate of Tn minus 1, it means that there exists, you can, define Fn to be the set of elements by which you translate Tn minus 1 to obtain Tn. Okay, so this is, now we define Fn to be these sets that, which are needed to translate Tn minus 1 to tile Tn. And now if you consider the finite product of copies of Fn with the normalized counting measure on Fn, well, then you can see that this decomposition here is giving you an isomorphism of measure space, of probability space, between this product here and T capital N with the normalized counting measure. So what it says, what this equivalence says, is something which is quite simple-minded. It just tells you that, well, because you have this sequence of decomposition, well, for any element in T capital N, there is a unique way of writing it as a product of elements of Fn. Okay. So here, if you think of, like Tn, we ask Tn to be a Folner sequence. So being a Folner sequence means that you almost have an action of gamma by translation. And it's not defined everywhere. It's not defined on the boundary, but it's defined almost everywhere. And so roughly, what's happening here is that if you look at this action on this almost action on Tn, what it gives, I mean, you also have an almost action on this product. And so this almost action on Tn, if you transfer it to this finite product, well, it gives you an almost, if you want, PMP action on this finite product. And what happens is that if you go all the way to infinity now, well, what you get really is an actual action, PMP action of gamma on this infinite product. And the fact that in the limit you get really an action is due to the fact that Tn is a Folner sequence, so that this almost PNP action, when you let n tend to infinity, really converges to a true action, which is very explicit. It's not, you don't need ultra filters or stuff like that to define this action. Is very, very explicit. And it's, some kind of odometer type. Yeah, and the point is also, which is quite interesting, that the equivalence relation that you get from these actions is actually the following one, which tells you that two sequences are in the same orbit if they have almost all their coordinates equal, all but finitely many. So that's a very natural equivalence relation on this infinite product, and this is exactly what you get. So now, if you quantify things, namely that if you have good Folner properties for Tn, especially with respect to their diameter, then you can obtain a quantitative orbit equivalence. So really the phi, the integrability phi, will depend in a formula which I didn't think would be interesting to write down here. But there is an explicit formula which tells you how integrable your coupling is, your orbit equivalence is, and this is going to depend on the diameter versus the ratio, the Folner ratio of Tn, which is somehow not very surprising. And it turns out that this construction gives you sharp estimates, sharp integrability conditions for instance, if you want to construct orbit equivalence between ZD and ZD prime. Well, it is sharp, I should say, well, not exactly sharp, because what it gives you is it gives you an LP orbit equivalence for every P less than D over D prime. So it's a little bit stronger than what is written here. Actually, what you get an orbit equivalence which is LP for every P less than D over D prime. But it would be really sharp if we could replace this strictly less by just less or equal. And so we don't really know what happens at D mod D, over D prime. This we don't know. And now for the Heisenberg and Z4, you get something which is really sharp, because you get that the coupling that you get here is going to be LP for every P less than 1. And here we know that for L1 it doesn't work by Austin results. And finally, you can iterate. You can also apply it to Weiss products. And as I said earlier, if you have a coupling between Z and the lamplighter, which has exponential growth, then you cannot get better than log. So here, unfortunately, we don't get something which is sharp, completely sharp, because we have a loss. There is a power 1 minus epsilon, and that's the best we can do. So it's essentially sharp. It's not exactly sharp, but it's not far from being sharp. So now there is another construction which I'd like to explain, which is somehow more general. It is more general on the one hand. On the other hand, it's also different, because the construction that of PMP action that we will get from this are going to be less explicit. So the idea is to start with the sofic approximation of your of a kilograph of G. So what does it mean? It means that we are going to consider a sequence of maybe let me follow my slide. So before defining the sofic approximation, let me just consider a directed S label graph. So it's just a graph. For us, it's going to be finite, such that the edges are labeled by letters in S, the generating set, and you want the oriented edges to be labeled by S. And of course, what you want is when you have an edge which is labeled by S, then the opposite edge is labeled by the inverse of your element. So now we are going to define G index R. This is going to be the set of vertices in our graph G, such that if you look at the ball around X of radius R, you're going to see exactly the same as the ball of radius R in the kilograph of G. Okay, so exactly the same labeling. And of course, so a sofic approximation is a sequence of label graph which approximates the kilograph in some sense. And so precisely, what it means is that for every R, if you look at the proportion of vertices, such that around these vertices in the ball of radius R, you exactly see the kilograph, then this proportion tends to 1 as n tends to infinity. So we have seen already an instance of this, which are just Folner sequences. So I'm going to write the normalized continuum measure of the set by a new index the set. So here, if I rewrite it, it says that the probability of good points, if you have good vertices, which look like the kilograph, is tending to 1. tend to infinity. So as I said, well, examples of such sofic approximations are Folner sequences. Folner sequences are S-label graph, and definitely by the Folner condition, most of the points which are, I mean, these GR here are going to be somehow interior points of your Folner sequence. And we know that by the Folner condition, these points, I mean, are most of the points of your Folner sequence. Another example is if you take a sequence of finite quotients of so G mod Gn, so Schreier graphs of G, such that let's say that your subgroups are nested, they are finite index and they are nested, and you ask that the intersection is 1. So that what happens is that whenever you fix some R, if you take a large enough element in your sequence, then all the points actually are going to be good here. So now the point is that so this is a well-known thing. So if you take a sofic approximation of G, and if you take a non-principal ultrafilter, then if you take the limits of probability spaces, which is known to be a probability space, it comes equipped with a PNP action of G. And the idea really is starting from two sofic approximations of two different groups, G and H, to starting from sequences of functions of maps from between your sofic approximations, is somehow to take a limit of your Fn and hoping that it's going to define an orbit equivalence between these PNP actions. So in order to find the right condition for these maps between the sofic approximations to define in the limit an orbit equivalence between these probability spaces, then you will have to assume that your maps are somehow respecting the coarse geometry of your graphs. So to be more explicit, so it's going to be a combination of two things. It's going to be the fact that your maps are not distorting too much the distances. And it's also going to be that this is going to be true, but not necessarily everywhere. It's just going to be true for, most points, because again, you have a measure. And so in the end, you want something which is defined up to measure 0. So the actual statement is going to incorporate both a probabilistic aspect and a geometric aspect. So it's a combination of geometry and probability. And so that's the reason why we call our property statistically by Lipschitz, for instance. So being statistically by Lipschitz is the condition that will ensure that we have in the end an orbit equivalence. So you see that the first condition tells you that Fn does not expand the distances too much. It's basically saying that it's essentially Lipschitz, but in a statistical sense. So what does it mean? If you look at this complicated formula, we only need to look at the first one because the other ones are kind of similar in nature. So you see that what do we look at if you forget about the two limits first and just focus on the mu x of blah blah. So what we are looking at here is the probability for this is the normalized counting probability measure on Xn. So the probability over the vertices such that Fn of, the diameter of the image by Fn of the ball of radius 1 around this X does not, is bigger than C. So C is an element that in the end is going to tend to infinity. And so you are saying that you want that the proportion of points X such that the diameter of the image of the ball of radius 1 exceeds a large number is tending to 0 as this number tends to infinity. Okay, So, but somehow you want this to happen in the limits. Okay. And so because you want it to happen in the limits, before taking the limit when c tends to infinity, you first take the limit with respect to the ultrafilter. So that somehow this, if you forget about the limit when c tends to infinity, what you are reading here is the probability in the limit that, if you want the limit of Fn, distorts the distance. Okay, so I hope this was sufficiently clear, at least the idea which is behind it. So then, of course, you are going to define similarly that you want also Fn not to contract too much the distances. So you have a similar property here. And so far we have only considered conditions telling you that you don't distort too much the distance, but it doesn't tell you anything about being surjective, so or even being injective. So the last condition ensures that Fn is going in the end, in the limit, to define a bijective map. So you have these three conditions. The two first ones are geometric, and the last one is only like sec theoretic, only tells you that it's bijective. So now the point is that if you take two sofic approximations, you take a map between G and N, Gn and Hn, then if Fn is used statistically by Lipschitz, then there exists the PIP actions are the ones we have defined so far. And the point is that they will have the same orbits. So there will be an orbit equivalence between these things. And you will have a quantitative statement, which is directly related to the conditions we had here. You see that when you say that the limit when c tends to infinity of this thing tends to 0, well, you may quantify this by saying that, if you fix c, then this is a certain function of c. And you are requiring that this function of c tends to 0 as c tends to infinity. So this is precisely what we have here. You see, this alpha of c is going to be this quantity I've just defined, and you have also a condition going the other way, involving alpha of c. So alpha of c is going to be this limit here that we've seen on the last slide. So once you have this kind of condition, you see, telling you that the probability that the distance is distorted is small, say, well, then you can convert it into an integrability condition. Okay, so that's not hard to convert this type of inequalities into an integrability condition. Yeah. So, okay, so now comes a natural inverse problem that you may ask, which was addressed by Amandine Escalier. So I'm not going to spend too much time on it because she presented her results last week, I think. But roughly speaking, the first question is, what can you do with Folner tidings? Like, can you show, for instance, that the isoperimetric profile is optimal simply using Folner tidings? And the answer is partially yes, in the sense that if you only consider couplings with the group Z, then that's enough. And the way she proved it was by using groups constructed by Brieussel and Zeng, for which the isoperimetric profile, or the Folner function is prescribed. So you take any function basically with some regularity condition like increasing or something like that, and Brieussel-Zeng produce for you a group, an amenable group, actually even an elementary amenable group, which has exactly this function as Folner profile. And so what Amandine managed to do is to construct a Folner tilings for these groups, which gives you the right integrability condition, namely the optimal integrability condition for a coupling with Z. And a more difficult inverse problem is where if you take two functions, two possibilities for the Folner profile, the Folner function, whether you can find two groups with these Folner profiles and with exactly the right integrability condition between them. So that's much more difficult. Doing it between G and Z, okay, Z somehow it's easy to construct Folner tilings, so it's only a problem about G. But now you have G and G prime. But first of all, you have to find G and G prime. Well, these are provided by Briosel-Zeng, let's say. And now you have G and G prime, and you have to find Folner tilings for each of them, and you have to match them. And that's much more subtle and much more difficult. But still, Amandine managed to do it not for all possible behaviors of the Folner profile, but for quite some wide range of them. So it was really a tour de force and really impressive work. Now, so what we have seen so far are couplings between groups which are as different as possible. You know, like you take these groups which are very different Folner profile, and you try to somehow, you know, like to bridge the gap, like to find an OE between them with the best possible integrability condition. But of course, because they have very different Folner profile, the integrability condition is going to be very, very poor. Okay. Now we may also wonder, well, if you take two groups which really look the same in some sense, in the sense that they have the same isoperimetric profile, for instance, and somehow they share some similarities, whether you can actually recognize it by the fact that they are almost quasi-isometric, like they have an exponentially or a very well integrable orbit equivalence coupling. So one instance of this is if you look at the Lamplighter group with the size of length, which is Z mod M, med M, and you look at the Bohm-Sachs-Solitar group. So the Bohm-Sachs-Solitar group is also an extension of Z by a subgroup, which is, well, somehow, I mean, I should have written it, but it's, I mean, both groups are metabelian groups. They have the same isoperimetric, the same Folner profile, which is exponential. And they really, you know, that they have the same asymptotic codes. They have very, very things which are very similar in some sense. And what we found out is that they are not quasi-isometric because one of them is finitely presented and the other is not. So the Lamplighter group is not finitely presented, but the Bohm-Sachs-Solitar group is finitely presented. So they cannot be quasi-isometric. So they are not that similar in some sense. But still, what happens is that they are exponentially orbit equivalence, which is very strong. Exponential is a very, very fast map somehow. So it's much stronger than being L1 or LP for NEP. So in particular, they are LPOE for NEP. And what's nice about it is that the way we constructed the coupling is very explicit. Unfortunately, I don't have time to explain it now, but it's somehow even more explicit than the Folner tiling technique. It's very, very, you can look at it in the paper. It's extremely transparent. And again, this construct with the fact that they are not L infinity OE, which would imply that they are quasi-isometric. Now you see that I've chosen M, the integer M, to be the same on both groups, and that was not just for clarity or something like that. It's really that there is a difficulty in changing this integer. And for instance, if I just take the Bohm-Sachs-Solitar group with M and the Bohm-Sachs-Solitar group with N, well, we know that they are not generally quasi-isometric. So they are not L infinity OE, for instance. But it still turns out that they are exponentially, so, okay, sorry, here, it's not OE, it's NE, it's stable, if you want. I'm not going to define it completely, but that's a variant of OE. And the thing is that, I mean, this is much more difficult actually to prove this than proving the first thing. And to do it, unfortunately, we cannot produce such a nice explicit coupling. We have to go through sofic approximations by Folner sets to produce this coupling between these two groups. Although somehow you may think that they are much more similar than the Lamplighter and Bohm-Sachs-Solitar because they are two Bohm-Sachs-Solitar. But somehow, you know, like they are more different, even though they are algebraically more similar in a sense. But geometrically, they are further away in some sense. And a question which is still open at this time, at least I don't know the answer, is whether they are OE ready. Here it's a stable OE. I'm sorry, I'm not sure what time I'm supposed to stop.
So probably, oh, I see, right. I think it's probably good to, you could stop around 3 or a little bit earlier to have
Okay. So I
more
have,
time for questions. Yeah.
okay, sure. So I have a little bit less than 10 minutes.
Yeah.
Okay, great. Actually, I'm going to be probably a bit earlier. So let me now focus a little bit on the case of nilpotent groups. So let me just go back. Let me remind you, maybe the first thing I'd like to say, yeah. So, no, sorry, this is even earlier. Yeah, I wanted to focus on these 2 results. So if I focus on nilpotent groups, these are exactly groups with polynomial growth, as we know by Gromov theorem. And so if we look at these 2 theorems, the one of Lewis and the one of Austin, what do we know already for nilpotent groups? Well, what these 2 theorems tells us is, well, first of all, that if you want them to be L1 or E or better than L1, then you need them to have the same volume growth. Okay, so that's one thing, but you have many nilpotent groups which are very different and have the same nilpotent growth, the same volume growth. Like for instance, the example I gave of Z4 with the Heisenberg group. But then Austin comes along and says something a little bit more precise for them, namely that if they are L1 or E, then if one of them is abelian, then the other one also has to be abelian. For instance, this rules out the possibility that the Heisenberg group and Z4 are L1 or E. Okay. Okay, so now let me go back to my slide. Oops. Sorry. Yeah. So with Delabie, we have studied a little bit more in details. So what happens for nilpotent Lie groups? So yeah, okay. So here I stated things for nilpotent Lie groups. We can do the same for discrete groups. It's a little bit more natural and more general to consider nilpotent Lie groups. But yeah, I'm not going to expand on this, but somehow this is a more natural setup. But of course, it requires to work with the locally compact groups, so it's a bit more technical. But yeah. So first of all, we know that G and G prime are NPOE for all P less than D over D prime. So that's a generalization of what I said for ZD and ZD prime. And this is obtained by you need sofic approximations to do that. Then we have that G and G prime are not LPME for all P larger, strictly larger than D over D prime. So this is you can use volume growth and the statement that I stated, but which is essentially due to Lewis. Okay, which is the volume growth condition. So yeah, so the thing that we don't know yet here is what happens for D over D prime exactly. Now we can say something for the cases when there are L1 and E. And the point is that when there are L1 and E, we know by Austin, so Austin's result, the true Austin result, says that if G and G prime are L1 and E, or OE, or here it's ME, but it doesn't matter. You may think of OE if you prefer. Then they must have same associated Carnot. So, or if you want, they must have the by Lipschitz asymptotic cones. So I'm going to give a very explicit example of what is it? I mean, what is the Carnot group associated to a nilpotent group? Okay, in my next slide. But now what we are able to do with Delabie is to prove the converse of that. So what it means to say that, you know that there is a very famous conjecture for the classification of nilpotent groups up to quasi-isometry. So the classification of nilpotent groups up to quasi-symmetries is one of the most challenging open problems in geometric theory right now. Many people have tried to solve it, and yet it's not known. But the conjecture is that two nilpotent groups, let's say simply connected nilpotent groups, are quasi-isometric if and only if they are isomorphic. Okay, so that's very strong. Of course, if you are isomorphic, you are quasi-isometric. Here, the conjecture is that this is an if and only if. Now, what happens is that, and what we know by Ponsu is that if G and G prime are quasi-isometric, then they have the same Carnot group which is associated to them. Okay, they have isomorphic Carnot group. So that's a weak version of the conjecture. But we also know that this is not an if and only if. Okay. Here, what happens is that for L1 measure equivalence, or orbit equivalence, it also works for orbit equivalence, you get an if and only if. So it's kind of a surprise somehow. It turns out to be easier to classify nilpotent groups up to L1 orbit equivalence than it is to classify them up to quasi-symmetry. So, and the condition is weaker, which is normal because L1, because quasi-symmetry here is basically equivalent to L infinity measure equivalence. So here the condition is that they are L1 and if and only if they have isomorphic Carnot group. And so again, the part which is due to us is the direction where we actually produce an L1 coupling between them when they have the same Carnot groups. And it turns out that we can do a little bit better than that. Actually, if they have the same Carnot groups, then we can actually produce an LP coupling, which is LP for some P larger than 1. So the P depends on the groups, okay? But we can always exceed 1. So that's also something which I find quite interesting. Now, the question is, what can we say about pair of groups which have the same Carnot groups? So I'm going to give you a very explicit, instead of giving you a general definition or whatever, I'm going to give you a very explicit example of pair of groups. One is not Carnot, and the other one is Carnot, and the other one is actually the Carnot associated to it. So I'm going to start with the Heisenberg group. So the Heisenberg group has a Lie algebra, which is spanned by U, V, and the commutator. So it's three-dimensional Lie algebra. The commutator of U and V is central, it commutes with U and V. And so that's the Heisenberg group. It is two-step nilpotent, and its center is spanned by U and V. Now, my second group is just a generalization, if you want, of the Heisenberg, where now my Lie algebra is spanned by X, Y, commutator of X and Y, and you take the commutator of X with the commutator of X and Y. So I'm almost done. So now this group is three-step nilpotent. Okay. And its center is, again, the last term of this. So it's the two centers are one dimension. Okay, so now I'm going to define a group, which is what's called the central product of these two groups. So I'm going to take the Heisenberg group. I'm going to take the direct product of the filiform group, and I'm going to identify their quotient. So I'm going to quotient by the relation commutator of UV equals this commutator. Okay. So what I'm going here is that I'm messing things around because I had a two-step nilpotent, which was Carnot, so it was graded. You have a grading, which is, you have the first strata, U and V, and then you have the second one, the derived subgroup, which is U and V. And you have this filiform group, which is also very neat. It's also Carnot, it's graded. So you have XY, the first strata. Then you have XY, you have the derived subgroup, the second term of the central series, and the third one, and it's graded in a very nice way. And now I'm messing things around because I'm identifying the center of the Heisenberg group, which is only in the second step of the central series, with the center of the other one, which is in the third step. So because I'm doing this kind of mixture, I'm just making this group not Carnot. Okay, so it's three-step nilpotent, but it is not Carnot. And actually, if I consider its Carnot group associated to it, what happens is that this Carnot group is simply the direct product of the filiform group with R2. So what does it mean here? What happens? So what happens is that the center of the Heisenberg group got swallowed by the center of the filiform group. Okay, and so actually what happens is that these groups turns out to be the asymptotic cone of my previous group. So because they have the same Carnot group, because one is the Carnot of the other, they have the same growth, and the growth is 9. And to compute the growth of an nilpotent group, you take the first, the abelianization. Here is dimension 2, U and V, or X and Y. Then you take the second. I made a mistake actually. It was not 2, it was 4. Whatever, my computation is wrong, I'm sorry. So forget about it. Sorry about that. So the result that we have with the Delabie is that we are able to show that these two groups are LPME for all p less than 3 halves, which is strictly less than 1. And what we can prove by a completely different method is that they are not LPME for p larger than 5. So in general, we are not able to show that two groups which are not isomorphic are not LPME, but here we are able to do it. And well, I'm going to stop now. Thank you very much.
Thanks, Romain.
I actually appreciate the very last slide. Of all the stuff I've read about the Carnot group, I've never seen somebody give a simple example like that, where you smash the commutators together so you mess up the grading.
Yeah, that's a very explicit and very workable actually example. That's kind of.
Yeah. I mean, once I see that, I realize, oh, you can do a lot of games like that because there's a whole lot of two-step classifications and things like that of nilpotent groups.
Right, absolutely. Yeah, you can construct a lot of examples in this way. Indeed. Actually, you really see what's happening here because if you think in terms of asymptotic cones, what happens really is that you understand what's going on here because you see that in the Heisenberg group, you can travel in the center at quadratic speed by using commutator. But in the filiform group, you can travel much faster because you are in the third term.
Because
so when you identify the centers, you realize that the Heisenberg group cannot catch up. And so in the end, it becomes R2, and that's it.
Yeah.
Well, let's thank Romain for a great talk.
Thanks.
There any questions? I have to go soon. Unfortunately, I'm a little bit pressed for time. Usually I'd like to have more time. Sorry, something came up. But are there any questions?
Is this the end of the line? I mean, your results seem pretty comprehensive. You're going to squeeze more out of it?
If I have more results?
Well, no. Do you think that this can be pushed further?
Oh, yeah. Well, yeah, there are a lot of things that could be done. So, well, if it's only about, maybe I present things in the way that gives the impression that we have, very cool results, but actually we know almost nothing.
Okay.
So in a sense, okay, we have this group that match, that show that the asymptotic that the Folner function is like sharp in some sense in giving you an obstruction, but it doesn't tell you much. For instance, if you take two polycyclic groups, they have the same growth, they have the same Folner function, but they may be very different.
Yeah. Okay.
If I take Sol, which is an extension of Z2 by Z. Or if I take, you know, an extension of Z2 with Z2 with two matrices acting on, I mean, you know, two actions, sorry, two commuting matrices or whatever, you know, we don't know. I mean, these groups should not be L1, ME, or maybe they are, I don't know. But
Okay. Yeah.
so, you know, like they are, the thing is that we only have the Folner function and the growth to distinguish these groups. And that's not enough. I mean, for instance, we don't know, we'd like to understand better what's happening with the for instance, the den function, the filling functions in general. That would be interesting to have something about them. Or the asymptotic dimension. So we already know that asymptotic dimension is not invariant. But, you know, maybe if you make it a little bit more quantitative, something is, you know, you want to distinguish groups which look relatively the same, but you want to have an obstruction. You know, to say that they are not, you know, even for the examples I gave, you know, I was advertising, maybe I was too much advertising this result, saying that these two things are exponentially OE. I was saying, oh, this is great, we have exponential OE. But this is not so great because maybe they are much better OE than exponential. And we don't know. And we are completely unable to say whether, you know, when does it start not being the case? If you take double exponential, for instance, does it still work? Probably not, but we don't know. The only thing we know is that it's not L infinity because they are not quasi-isometric. But that's the only thing we can say. And, you know, and a lot of situations like that where we really don't know how to, I mean, what is missing really now is more at the level of obstructions. We don't have enough obstructions. We don't have enough invariance. And so this is really something we have to work on.
Okay.
That's interesting. Also, if you have just a single group, fixed group, and you have, you know, you can have two actions that are not LP orbit equivalent, you know, because of the structure of the actions themselves. I mean, I'm guessing that the actions that you construct to show positive results, you know, to find nice orbit equivalences, a lot of them are coming from the sofic approximations, which to me suggests that they're very complicated in some sense. They're
well, except the ones that are coming from the Folner tilings, because these ones are profinite.
Yeah, right. Those ones are profinite.
Yeah. I know that's a very, very good question indeed. So as you say, I mean, here we don't, we would need to complement this by understanding indeed even for the same group. So we started actually thinking about this problem for Z. With we have another, so that's another talk. But for Z, we started, you know, trying to show some flexibility result because we have Belinskaya result that you know, I'm sure, which says that for Z, if you take an L1 orbit equivalence, then that's an isomorphism. But if you just go just below L1 for any function which is sublinear, then you can produce, for instance, you can show that you can produce actions. One is weakly mixing and the other one is not, or something like that. But still, I mean, this is far from a complete understanding of what's happening. So, for instance, a very natural question is, what can we say between two odometers with different values? You know, what about the odometer and the Bernoulli, or two Bernoulli shifts? So, I mean, this we don't know anything basically. So that's very interesting, and that's interesting for Z already.
Yeah.
That's an orthogonal direction, but which is as interesting.
Yeah.
That's really open. That's very, very open. I don't want to sound like we solved everything. I mean, this is far from being the case. And I'm very happy to have new students jumping into the subject. There are a lot of things to do. I think it's a fascinating subject. Really.
Well, let's thank Romain again. Yeah, a very interesting talk.
Thank you for your question and for the invitation.
Yeah. Thank you.
So I guess that's it. We're taking a break next week, but we'll be back on the 21st of October with a talk by actually Francois Lemaitre. And then on the 28th, we'll have Ben Hayes.
You are invading
So-
the French connection.
Yeah, that's right.
Okay, thank you very much.
Okay,
Good day.
it's.
Bye.